Hi, Ben. Hi, everyone.
Hi, how are you?
Very good. How's it going? It's freezing in Austin, which is very unusual.
Oh, yeah, I see. Right.
Hi, Nathanael.
Hi. Oh, this is nice to see you. I think you know about this work, Yuval.
Yes. Oh, yes, I've given the talk many times, but it's nice to see how others present it. So, how are you?
A bit tired, but like many people, I think. But okay, it's been worse. So, and it could be a lot worse, obviously. So,
well, hopefully it will get better.
one can hope. Start sharing. Do I already have sharing permissions, Luis?
Yes.
All right, so let's try this.
Anyways.
Hello.
Hi, Klaus.
Hi, Luis. Hi, Yuval.
Hi, Alex.
Hi, Yuval, Manishma, how are you?
Okay.
How life in California these days?
What?
How life in Seattle these days?
I'm not in Seattle. I'm actually in Ohio.
Where are you now?
Yeah.
You are in Israel now?
No, I'm in Ohio.
Ah.
And where are you? Are you talking from Jerusalem or where?
Yeah, I'm back in Jerusalem. I was for 3 months in Princeton from September till December, but it doesn't matter. I was in Zoom there and I'm in Zoom here, you know, these days. We live in the Zoom, it doesn't matter. I went there to be at the Institute, but I was not there, you know, I was in their apartment, but it was the same as doing it from Israel or doing it from there.
Yeah.
But at least here in Israel, we already been vaccinated, so we maybe see the light at the end of the tunnel, though who knows?
Awesome. Also.
I wouldn't call it the end of the tunnel. You're probably going to be the world's first major petri dish for developing vaccine-resistant strains.
You know, by the way, what's the reason that Israel got it first? We are kind of the how you say, the pigeon neck for the world, because Israel is actually an empire of a medical database, because the medical service was a kind of a national one, even before the state of Israel, when there is a very good record. And then the company Pfizer, and Israel is small enough to do the whole country and not too small that it's really meaningful. So they really wanted to have such a country that they can make all the statistic and everything, and having records backward in case of problems, etc. So at this point, it looks good. Who knows?
So, Nathanael, are you ready? I guess we should.
Yeah, in principle, yeah, happy to start.
Okay, let's get started. So we're happy to have Nathanael Berestycki from the University of Vienna. Talk about cutoff phenomenon on random graphs.
Okay, so welcome back, everyone. So thank you for coming back. Last week we talked about the cutoff phenomenon, and I mentioned some I think fascinating questions in this area. I just wanted to say before we start, today we're going to talk more about random graphs and their geometry and their limits than about cutoff, but eventually we're going to bring these two themes together towards the end. I just wanted to say that today, in fact, on Archive, there was a paper posted which talks about some of the questions I've mentioned last week. So I highly recommend, there's a paper by Justin Salez that was just posted that seems like a very, very nice paper, and which talks about some sort of conditions, generic conditions for existence of cutoff. So that sounds like a very exciting progress, and I hope I will have the chance to read it soon. So today, what we're talking about will be some random graphs models. So I will talk about the most simple models of random graphs one can think about. So these are called Erdos-Renyi random graph. These are called GNP. Probably many of you have heard of them. If you haven't, that's totally okay. So I'll go slowly about them. So in this random graph model, we have two parameters. We have n and p, and usually this graph is called GNP. So n is just a number, and p is a number between 0 and 1. And what do we do with these two numbers? We start with n vertices, and then we decide that we're going to include every possible edge in this graph. There's a total of n choose two possible edges in this graph, and every edge, we're going to draw it with probability p independently of one another. Okay, so every edge is present, yes or no, we toss a coin with probability p. Okay, and that's, gives you a graph, G and P. Here's a drawing of this graph. And I guess the most basic question you can ask is, what is the geometry of this graph? It's a random graph because we toss coin to draw it, but what is the typical geometry of this graph when n is large? And we think here as a function of p. So this is this is maybe one way to think about it. If you just search for this on Google, you'll find lots of softwares that proposes. It's very easy to draw, obviously. So I did that myself this morning. Can you see this? No, it doesn't look like you can actually. Are you seeing a web page, or are you still seeing my slides?
We're seeing a web page, but nothing on the web page. I guess the 0 edges.
Okay, so let's see if this works. Maybe I should take.
We can see some vertices.
Yeah. Okay. So that seems like it's working. Okay. So I didn't see this correctly. So, so here there are currently 27 vertices. So I'm just gonna add more nodes to this graph. Let's increase the speed a little bit. Let's make it about. So I just found this on the web this morning. Okay, so when I was preparing, so let's have roughly 500. I don't know. Okay, that's good. Good, and so that's the vertices. And now what I'm going to do is I'm going to add edges sort of one at a time. In the version I was presenting, every edge was included with fixed probability p. And one way of picturing what happens when you increase p is that you add more and more edges, and these edges come uniformly at random. So I'm going to start adding edges, and we're going to see how this changes. And basically, the more edges you put is basically the same as increasing the value of p. So this is what looks like happening. So let me reduce the speed. We've got, let me pause for a second. We've got, at this point, we've got roughly 100 edges out of 500 vertices, and you see that the component sizes, they're all quite small. So let's keep going. Can I do that? No, maybe I just have to, okay, there we are. So then we keep adding edges, and roughly speaking, the picture stays essentially the same for a little bit, and then you can increase the speed a little bit to see something happening. And hopefully, you know, as more and more edges are added, then the component structures become more and more complex. And eventually you start building up fairly sizable components, connected components.
Nhưng mà vấn đề mới đang nghe talk mà. Chịu được không? Được không ba?
And eventually, you know, we're roughly at about half the number of edges, number of vertices here. And you see that already you start having connected components that are, you know, pretty big. I'm not sure how big they would be, but you know, I would say, you know, comparable to the size of the graph, to the number of vertices. Somebody asked me, what is this website? And I'm happy to send it to you directly by the chat. Let me do that. So this way, if you're bored during the talk, you can play with this. There's a lot of very nice visualization software on this website. I don't know who did it. This is just the first Google hit I got. Okay, so you know that gives us an idea of what's going on. You increase p, and then all of a sudden something happens. The components, they were all small, and all of a sudden they become big. Right? So that's the phenomenon that we want to discuss, and it seems to happen. At least, you know, there's, I said half because I know the theorem, but at least comparable, the number of edges is comparable to the number of vertices. Okay, so let's go back to the slides. So again, this was our question. What is the typical geometry of this graph as a function of p? Okay, so there's something in the chat. Let me see. All right, good. Yeah, I may not see every question in the chat, so please, if I don't see it, feel free to interrupt me. Okay, so here's the very nice theorem that basically started this topic. So fundamental result of Erdos-Renyi in 1959. So there's a natural scaling here, which is to take p to be of the order a constant over n. We'll call that constant lambda. And the reason this is natural scaling is that, simply speaking, simply puts the expected degree of a vertex. Oh, okay, it's not equal to lambda, but it converges to lambda as n tends to infinity. So you have an expected degree, which is a constant lambda, and that's why this is a fairly natural scaling. And so the theorem of Erdos-Renyi is that there is what they call the double phase transition at lambda equals 1. So to state that, what I will do is I will call C lambda the largest connected component in this graph, G and P is now chosen to be lambda over n. So the theorem is that if I consider the size of this component and I rescale by n the total number of vertices in the graph, so obviously this is a quantity between 0 and 1, the theorem is that this converges to a number, theta of lambda. So this number is a function of lambda, the average degree of a vertex. And the theorem is that this limit is strictly positive if and only if lambda is greater than 1. So when lambda is greater than 1, you've got one, it's called the giant component, this thing. You've got one giant component whose size is a fixed proportion of the entire graph. Whereas in fact, it can be shown that the second largest component would be much smaller, basically logarithmic. And then, right, so this is what's happening when lambda is greater than 1. When lambda is smaller than 1, then the biggest component is tiny, basically logarithmic. And at lambda equals 1, there is a very interesting scaling, which was partially understood by Erdos-Renyi, but finally completely understood in a landmark paper of David Aldous in 1998. So yeah, so as you increase lambda, again, for lambda smaller than 1, the components are tiny, microscopic, largest one is only logarithmic. At lambda equals 1, you've got an interesting scaling with a size of roughly n to the 2/3, and lambda greater than 1, a fixed proportion of all the vertices in this unique giant component. Questions so far? So that's a theorem, and what I'm going to spend a little time to tell you why that's true, where this comes from. Okay, because I think it's a very nice story and simple to understand, and it fits very well with your topic of Benjamini-Schramm limits. And maybe this will be the first time you really we talk about a Benjamini-Schramm limit that is interesting.
Sorry, one quick question.
Yeah.
What exactly does it mean? The convergence, does it mean like with probability 1 or something?
So good question. So what it means, okay, so obviously, the size is a random variable. So what it means is convergence in probability. So what it means is that it's unlikely the probability of being far away from the limit tends to 0 as n tends to infinity. Okay, so the probability that that minus its limit is greater than epsilon, that tends to 0. So it's very unlikely to be far away from the limit I said it was. That's the meaning of the statement, as n tends to infinity. Yeah, I'll thank you for asking this. I might not be so precise later on because I will mostly try to convey some sort of big picture ideas and hopefully convince you of why some results might be true. And the main goal is that at the end, people feel like they've understood something about the geometry of these graphs. Right, so I'll try to say something about where that theorem comes from. And as I said, the idea is really to try and understand what is the Benjamini-Schramm limit. So obviously it was not formulated like that in the original paper, but it's a very natural idea that simply asks the following question. So let V be a fixed vertex, might be vertex number 1, for instance, and let fix lambda strictly positive. And what we're going to try and describe is what does the graph look like close to V. Okay, so that's what it means to ask what is the Benjamini-Schramm limit. So I have my vertex V here. Maybe let me put a picture, and I'm going to ask myself, what is the law of what I see in the neighborhood of size 1, in the neighborhood of size 2, in the neighborhood of size 3, and so on and so forth. So in general, I'm going to fix myself some number. I'm going to consider the ball of radius r in the sense of graph, so the graph distance ball of radius r, and ask myself, what do I see in this ball? Does the distribution of what I see in that ball converge to a limit? Okay, so that's what it means. It means to ask ourselves, what is the Benjamini-Schramm limit of this graph? Okay, so the first question we've got to understand, obviously, is what is the degree of this vertex? Okay, so that's going to be the neighborhood of size 1. And if I can tell you that there's a limiting distribution for the degree of the vertex V that I've chosen at random, then that's a good step. We'll have shown convergence in the Benjamini-Schramm sense, at least for r equals 1. Right, so what is the degree? Well, it's quite simple. Really, it's very explicit, because if I ask myself the probability that the degree is k, well, I've got to choose those k vertices, who they are, and there's n-1 possible choices. And then the corresponding edges, they need to be open, and all the other edges to which V might be connected, they need to be closed, right? So that's just that. And then, it's a very simple computation. Basically, I'm saying that dV is a binomial with n-1 trial and success probability lambda over n. And as is well known in probability, and this is a totally obvious computation, this thing here converges to e to the minus lambda, lambda to the k divided by k factorial. As n tends to infinity. And this is the distribution, this is the probability that a Poisson random variable with parameter lambda or mean lambda is equal to k. So we have here with this simple computation shown that in the neighborhood of size 1, the distribution of what I see around V, that converges. I have a limit, which is a Poisson number of neighbors. Okay, and then the idea is very simple, which is, so I need to ask myself, what about larger neighborhoods? So what about, let's say, neighborhood of size 2? So the idea is simply that I can iterate this. So, if I ask myself, what do I see in a neighborhood of size 2? So suppose I tell you who were the neighbors of V. So we have V here, and we've just discovered, I don't know, 3 neighbors of V. So here's V1, here's V2, and here's V3. And if I wanted to understand the neighborhood of size 2 for V, then I need to understand the degree of V1, and I need to understand the degree of V2, and the degree of V3, and that's it. And basically, it's essentially the same computation. Okay, so with same computation, again, this degree for V1, it will be binomial with maybe not n-1 trial, but n-3 trials or 4. Okay, so degree of V1 here will be binomial, n-4, and then lambda over n. Degree of V2 is same thing, and these are independent. So we find, okay, and it's +1 because there's this edge that we already know is there, right? Right, so the same computation tells us that actually what we see in the neighborhood of size 2 has a very simple structure. We start by generating a Poisson number of neighbors, and then each of those are going to be connected to a Poisson number of neighbors themselves in the limit, and these numbers are independent. So here I have a Poisson number of neighbors that's independent, here another one, and here another one, and these numbers, they're all independent of one another. This independence is inherited from the independence of the edges.
So shouldn't that be
I think
n-2?
Yeah, I think the n-4 should be n-2.
Yeah, we're
Right.
just eliminating 2
So-
vertices.
Okay, good. So these are obviously details. They don't matter in the limit, obviously, but
Yeah.
why is it really n-4 is because I've really revealed already this one. Okay, yeah, no, you're right. It is n-4.
Yeah, there may be edge from V1 to V2,
You're right, of course, it is.
for instance.
You're right. Thank you. Very good. You're right. In principle, it's also possible that there's an edge happening there, but
Yes.
you just won't see it with very high probability, right? The probability that you would see an edge like that just disappears in the limit because it's of order 1 over n. Okay, great. So that's very good. So So this is to summarize what I've just explained. We have a convergence in the Benjamini-Schramm sense for the random graph. And the limit is an interesting object, namely, I have what's called a branching tree. So this is also called a Galton-Watson tree. But I'll call it a branching tree for simplicity, where the offspring distribution is Poisson with parameter lambda. So again, let me just state it again. We start with V, which is the root of this tree. Then everybody gets a Poisson number of offspring, and then so on and so forth. And all the offspring variables, they are all independent of one another, and and they all have this Poisson distribution with parameter lambda. Now, the point is that depending on lambda, something happens in this Benjamini-Schramm limit or not. Namely, this tree could be infinite with positive probability, but that can only be the case if lambda is greater than 1. So this is a small theorem about branching processes, but I believe one that we're all acquainted with these days with the virus, because lambda in today's world is called R, the reproductive number. This is, you have the virus, then you give it to a random number of people. How many on average? Well, R, or lambda in my case. And then these people transmit the virus again to a random number of people, again with the same mean. And what we're all obsessed with is whether R is less than 1 or greater than 1. Why are we obsessed with this? Because if R is greater than 1, then the epidemics might survive, right? It might propagate to a very large number of people. And this is exactly what we're worried about. And this proposition, this simple fact about Galton-Watson trees tell you that indeed, when the mean degree is greater than 1, then there's a positive chance that this thing will never die out. And in fact, and I mention it here because this will play a role later in what I'm going to say, if you call Zm the size of the tree at the mth generation, okay, so here we had Z0 equals 1, here it was 1, 2, 3, so 3, and then I don't know, 2, then 1, 2, 3, 4, 5. Okay, so this is Zm, the size of the tree at generation m. Then the Kesten-Stigum theorem, which is a fundamental result in the theory of branching processes, tells you that the size of the mth generation of this tree grows like lambda to the m. Okay, and in fact, if you divide by lambda to the m, then this size converges to a non-trivial limit. This limit is positive when the tree survives, when the epidemics never dies. So this is saying when the tree survives, not only do I infect an infinite number of people eventually, but I have an idea of how fast does the epidemics grow. At the nth generation, I've infected roughly lambda to the m individuals. That's how fast this tree grows. Any questions so far?
So, okay, so is the picture, but this is what you call the big component or something, this is somehow what's happening at every vertex in the set, right?
So this describes just the limits of what I see as n tends to infinity around a fixed vertex.
Okay.
So around the fixed vertex, what I see in the limit as n tends to infinity might or might not be infinite, depending on whether lambda is less than 1.
I see. Okay.
Does that make sense?
Yeah. But in that case, there could be many little components or something, right?
Exactly. Very good. I will explain that in a second. So you're absolutely right. To show the theorem, I need to say more. Okay, to show the theorem that said that there was really a unique giant component, I need to say much more than what I've just said. I will say it in a second.
Okay.
But at least what we see already now is that when lambda is less than 1, there is no chance for a giant component to exist. Okay, it's just not possible. If there was a giant component, then it would be the case that around many vertices, there would be a positive probability that what I see around a fixed vertex contains an arbitrarily large quantity. So it's at least for lambda less than 1. Already here, we've proved the part of the result concerning lambda less than 1 that there is no giant component, that this theta of lambda is equal to 0. So yeah, so to finish kind of the proof, we need to show basically that all those vertices for which the corresponding to trees that survive, they in fact, in the graph, they are really connected with one another. Okay, so I hope this is clear. This is exactly the question that was asked. If I have a limit for which the limit is infinite, how do I know that really in the graph at finite n, this corresponds to a point in a component of linear size? So an argument is needed for this, and I will only sketch it. I will not give a full proof. But the idea is the following. So let's take two vertices V and W. And I'm going to, so CV and CW maybe was not a great choice of notation. I'm thinking here of the component containing V and the component containing W. And I'm assuming that the sort of, in the limit, they correspond to points for which the trees survive. They are infinite, these trees. And what I want to show is really that in the finite graph, the corresponding components, they are connected. They are the same connected components with high probability. So if I've shown that, I hope you will believe that somehow the result I was mentioning at the beginning is true. So this will show that, so why is that? So it will show, namely, it will show the theorem that I stated from Erdos-Renyi with an explicit value for the limiting function theta of lambda. Basically, theta of lambda will just be the probability that the tree survives, where the tree is now this random branching tree. Right? Is that clear? Is that clear that if I've shown this, then somehow the theorem should be true, should be plausible? I see some people scratching their heads, so that probably means I need to explain this a little bit.
No, it seems, yes. This part is good.
This part is?
I'm a little bit confused about survival. I mean, I know in the what it means to survive in the branching process. You get something of infinite size.
Yeah.
I don't know what it means to survive in a finite set.
Yeah, that's a yeah. To say it really what it means, I would need to say to go more into the detail of what it means, but and probably it's not okay. Maybe I shouldn't. But what I can say is that technically what happens is that there is a coupling. So there is both the component containing V, CV, and a tree, and you can realize one as a subset of the other. You can arrange for things in such a way that the connected component containing V is always smaller than the infinite tree. So basically, the reason why that is, if I declared everybody to really have, to keep having exactly the same distribution, binomial with parameter n-1 lambda over n, then when I do that, I'm doing an overcount. So I'm counting edges that might not really be there. And so in this way, I've really got a branching process, and I've really got a connected component in such a way that the connected component is smaller than the branching process. And when I've done that, it means something to say that V is in a connected component that for which the tree is infinite. Another way to put it, which is maybe more simple and more concrete, is that I can just say that the connected component containing V exceeds any finite size. So you can put it this way. Let's assume that the component containing V is greater than 1,000,000. Okay, so let me just say that. This is maybe simpler to understand. So instead of that, suppose that their size is greater than 10 to the 6. Okay, 10 to the 6 is fixed. We all understand what it means. And now let's show that CV is equal to CW with a probability which is small when 1,000,000 is very large, which with a probability that is 1 minus something small when 1,000,000 is really made large. Does that make sense?
Yes, thanks.
Probability greater than 1 minus epsilon, depending on the million.
So we're taking the limit as a million goes to infinity.
Yeah, so there's a double limit if you want. Okay, so what happens is the following. So there are two steps, two ways in which one can see that. And there are two things one need to say. The first one is that if these components are really greater than a million, then there's a good chance they will be each greater than roughly square root n. So with high probability, with probability greater than 1 minus epsilon a million. And really, that's a consequence of what's called the birthday problem, which is the following question. You know, if I keep sampling from the same set, how long will it take until I see some repeats? And the answer is roughly square root of n. Okay, and it's an elementary computation, which I don't want to do, but it's a very simple fact that you can do in first year probability. So if I keep sampling from the same set, before square root n samples, I will not see a repeat. All the samples will be distinct from one another. And in particular, this says basically that when you approximate the connected component of V by the tree, you don't make much error until you've sampled, until you've seen of order square root n vertices in the connected component. So, okay, so I don't really want to explain that. It's not very complicated, but it involves a few ideas. And so the situation is the following. So we've got this V, and what, without too much effort, is that with high probability, these V's, they contain a connected component of roughly square root n individuals. And here's W here. And we can discover the connected component containing W at least until we found square root n individuals without too much problem. And the question now is to show that, in fact, these two sets, they are connected with high probability. And what you can see is that, you know, this seems reasonable. So why is this reasonable? For instance, you know, there's square root n, roughly square root n vertices on this side and roughly square root n vertices on that side. So the total number of possible edges is n, square root n times square root n. And each of them is present with probability 1 over n, or lambda over n. And so, you know, there's going to be a fixed chance for an edge to exist directly connecting these two sides. And, you know, if that edge is not there, then you've got a chance to repeat by exploring just a bit more of the graph. Okay, and so very quickly, in fact, what you will see is that you will find a connection. And so this is the step 2, which says that really the connected components, they intersect. So what we have shown is that if these two connected components, they are big, then in fact they must be the same. And so that shows, if you want, that there is a unique giant component. So that was a very sketchy, you know, I didn't want to give a full proof, but at least an idea of where the result comes from. And we learned something very interesting about the geometry of the graph when we see this proof. One thing we learn is that you know, what is the typical distance between these two vertices V and W? I claim it's roughly given by log n divided by log lambda. And why is that? That really comes from the Kesten-Stigum theorem, because if you think about it, you know, what was the number of generations you needed to grow the tree in order to reach roughly square root n vertices? Well, you know, to find that out, we need to know how quickly the tree grows. And if you remember, by generation m, you got lambda to the m vertices. So if I want lambda to the m to be roughly square root n, then m is roughly 1/2 of log n divided by log lambda. So this distance is roughly 1/2 log n divided by log lambda. And you've got the same thing on the other side. And together, the distance between v and w will be log n over log lambda. If you want, another way you can think about it is that you can seed from v and start growing your tree, and you just pretend that your connected component is exactly a tree. And you ask yourself, how many generations do you need to grow your tree in order to see roughly n vertices? And the answer is log n over log lambda, because the tree grows exponentially at rate lambda. Very simply. Okay, so this is a sketch, but it's an interesting thing that one can understand. So I hope maybe for your seminar, you get the perspective that thinking about Benjamini-Schramm limit, one understands a lot of interesting quantities, even global quantities, or even global geometric properties of a graph. Even though a priori the notion seems very local.
That's very nice.
Okay, so okay, good. Let me tell you about now really the goal of the talk. And the goal of the talk will be to study the random walk on this graph, C lambda. So C lambda is going to be the giant component. I'm going to take lambda greater than 1 and ask myself, what does the random walk look like on this graph? Maybe the most natural question for us as probabilists will be to think about the mixing time of the walk on this graph. And I should say maybe that for applications, it's not so, it's not such a stupid question to ask, because you might know that these random graphs, they have something to do with the structure of the World Wide Web. For instance, many graphs in nature are related to these models. And so, you know, your random walk on the graph, you can think of it as being Google exploring the graph and wanting to know how long does it take before it has really reached a steady state in its exploration. So this is a natural question. And this was answered around 2008 in two essentially simultaneous papers, one by Benjamini, Kozma, and Wormwald, and the other one by Funtulakis and Reed. And the theorem says that if you start from the worst possible starting point, if you remember when we defined mixing time last week, I made sure to say that we consider the total variation distance starting from the worst possible state. So from the worst starting point, if I ask myself, how long will it take until I'm reasonably close to the invariant distribution? The answer is roughly log n squared. And perhaps a bit disappointingly for us, there's no cutoff. And I say disappointingly because I think we like cutoffs. At least I do. And so there's a very nice geometric explanation of why that is. And I don't know if this word hairy expander is actually in the paper by Benjamini, Kozma, and Wormwald, but if it's not, it should be there. So they have a way of describing the giant component as follows. So there is one big piece, let's draw it like that, which is essentially an expander. So I think many of you know what expanders are, and I don't really want to define expanders. So much of it is an expander, but it's not just an expander, it's a hairy expander. And why is it a hairy expander? Because it's got hairs sticking out. That's what makes it hairy. And so that's what it looks like, roughly, schematically, that's what it looks like. This hairy expander is of the order of, in diameter of log n, but these hairs, they are themselves of order log n. So for instance, if you think about it, it's quite possible that the vertex v that you start from, it is connected to the giant component simply by having a path of length log n. Okay, so just one vertex, degree is 1 all the time. You know, there will be some vertices that do that. They're a bit exceptional in some sense, these vertices. It's unlikely that to have such a long hair. but they exist. And because they exist, if you start doing random walk from the worst possible starting point, then actually the worst possible starting point is located on one of these long thin hairs. So if you start random walk from there, just because it's basically a one-dimensional object and its length is log n, it will take roughly log n square to get out of that hair. And then once it's in the main part of the graph, so in this expander is very well connected. That's what expanders are. And therefore, the walk will mix very rapidly. So they have an argument to say that, really, that if you have a part of the graph where the mixing is slow and a part of the graph where the mixing is fast, then the slow part is what matters. And so that's where log n squared comes from. So that's just diffusivity of random walk in one dimension that tells you that. And why is there no cutoff? It's related to the fact that in one dimension, there is a scaling limit. We discussed that last time. And so the mixing time, the mixing does not occur in an abrupt fashion. So maybe this is a very short summary of their proof. So in a sense, it's disappointing. And maybe one thing that was a starting point of this project that I'm going to describe with Eyal Lubetsky, Alan Sly, and Yuval, who is in the audience, was the following thing. Okay, so these two papers that I just told you about, they tell us how does mixing occur from the worst possible starting point. But in some sense, these worst possible starting points, they are very exceptional. They represent a bad behavior coming from part of the graph that don't represent maybe what we think is a typical geometry of the graph. And so the question we started asking ourselves was the following. If I have a typical point, so let's take some vertex V and let's make it typical by just conditioning it to be in the giant component. So what can we say about the behavior, the mixing properties of random walk started from that fixed vertex? So I'm no longer going to maximize over the worst possible starting point. I'm not going to be interested in that. I'm just going to ask myself, how long does it take starting from that fixed vertex to approach the equilibrium distribution? And this is a different question. And what we show, this is the content of the results that I'm going to mention now. The main result that I want to discuss is that actually this has two effects, starting from the typical point rather than the worst possible starting point. On the one hand, the mixing time is much quicker. Instead of being log n squared, it's now roughly log n. And second of all, it is concentrated. So its value does not, the mixing time at level epsilon does not depend on epsilon. It converges to a constant, divided by log n, this converges to a fixed constant that does not depend on epsilon. And therefore, the cutoff phenomenon actually takes place. So the message is, if you start from the worst possible starting point, it takes a long time to mix and there's no cutoff. But if you start from a fixed typical vertex, then cutoff occurs and it takes much quicker to mix. Are there questions on this?
By typical point, you mean that this is in the giant component?
Exactly. So typical meaning that I didn't consider something, on the hair. I just condition it on being in the giant component. And because this giant component is, all the vertices play a symmetric role somehow. When I've made this conditioning, it's just a typical point for this component.
Is this? I'm just kind of curious if the mass of the hairs is larger than the mass of the core, or if it's like really small compared with the mass of the core.
Good question. It's very small compared to the mass of the core. If it wasn't, that would be wrong, what I was saying.
Yeah, okay.
Yeah, if it was big, comparable to the overall size of the graph, then like the typical starting point and the worst starting point would be comparable.
So it's, okay, so it's relative, so the relative mass of the hairs is going to 0.
guess the question is, what do you mean by hairs? Because there are hairs of constant length that are a positive mass, but the hairs of log-n are
long hairs, yes.
I understand.
But
Okay.
there is a concrete definition of hairs in this paper. So, and for that concrete definition, the relative mass really does go to 0. Anyway, I see that I'm a bit running very low on time, taking much more time, but maybe that's good. Let me say that there was roughly at the same time, in fact, simultaneously, let's say, the difference in dates is due to publication. There was a similar result for non-backtracking random walk, which let me not get into this too much, by Anna Benhamou and Justin Salez.
Let me see if I understand this correctly. If you start at a typical spot, it takes log-n time to explore everything equally. But if you start in a very bad spot, it might take you log-n squared time to escape and get to a good spot, after which you're going to explore everything very quickly.
That's right. That's right, exactly. If you basically, the message is here. So if you start anywhere in the good part, then mixing is quick, basically log-n. That's in fact what this theorem quantifies, if you want. But if you start from one of the bad part, just because it's going to take so long to get out of this thin part, log-n squared, then mixing is going to be slow. And then once you make it back into the core, then mixing is going to be very quick. So you're basically at that time scale, you will be instantaneously mixed. That makes sense? That's the picture to have in mind.
Yeah.
Okay, good. Thanks for these questions. Let me say that the constant that appears in the statement of the theorem, it's an interesting and somewhat implicit constant. The constant is defined really from the Benjamini-Schramm limit. So they are defined in terms of these trees. And what I was hoping to do, but I don't know how much time I'll have, is to tell you what these constants are and why they play a role in this problem. So to tell you that, I need to first make a detour via another notion of random graph, which is also very interesting in its own right. In some sense, a bit easier to think about. And this is a notion of random regular graphs. So what's that notion? We're going to fix some number d greater or equal to 2. And gamma nd is going to be a random regular graph with degree d. So what does that mean? We consider all possible graphs on n vertices where everybody's got degree d. There's a finite number of such graphs, and we pick one of those uniformly at random. So among all possible graphs where every vertex has degree d, pick one of those at random, uniformly. So that's a random regular graph with degree d. And as I was saying, it's, if you have a random graph like that, the first thing you need to do is to figure out what does it look locally around the point, meaning what is its Benjamini-Schramm limit. And it's not very hard to figure out that this Benjamini-Schramm limit, in this case, should be a DRE tree. So just instead of a branching process, so let me draw d equals 3. Etc. etc. Guess for certain values of d, you can think of a free group. Okay, and so okay, so this is a DRE tree, and it's not hard to figure out that this ought to be the case. So essentially, what I'm saying is that in a small neighborhood around the point, you won't see edges going from here to here. So you won't see, just like in the Erdos-Renyi case, you will not see these kind of edges that connect points that are close by, close to the fixed vertex V. And because of that, if you ask yourself, what should be the diameter of this graph? What is the maximal distance between points? then we can understand it in the same way that we did before, basically in the Erdos-Renyi case. So now we've got a DRE tree. This tree grows also exponentially. The rate is not lambda; it's d-1 now, and so the diameter you guess should be log base d-1 of n. And there are many things you can figure out from this graph by thinking about that. For instance, maybe let me not spend too much time about this, but you can guess this way that it ought to be weakly Ramanujan. So I don't want to go into Ramanujan graphs, but this means that the spectral bound, for the second eigenvalue, there's a worst possible value, and this is actually attained in the limit as n tends to infinity with high probability. This was a conjecture of Allen in 1986 and proved also in 1986. That doesn't sound right. Maybe I didn't get that correct. By Joel Friedman in 1986.
I think the Joel Friedman one is in the 2000s.
I think this, I must have made a mistake. I think, maybe, yeah, this doesn't sound right. Maybe this is in the 2000s. That seems more correct. Yeah. So let me start by asking a question, which is, how does random walk on this random regular graph look like? And one sort of naive hope that you can make is that this random walk will look like a random walk on the DRE tree, provided that you're looking at distances that are much smaller than the total diameter of this graph. So here's an example of this phenomenon, and this is something that I had proved with Rick Durrett in 2005. And this result says the following. So suppose I start from a fixed vertex V in this graph, gamma. So gamma is my random regular graph. I start from a fixed vertex V in this graph, and I consider the position of a random walk at a time t, which is roughly log n. And I ask myself, how does the distance grow? So the theorem is that this grows roughly linearly at the beginning and then stays fixed. So let's try and illustrate what that means. What is the phenomenon here? So here's V. Here's my vertex V. And here's the graph viewed from the point of view of V. So viewed from the point of view of V, it looks like a DRE tree, well, d-1 array tree. And so this grows and grows and grows until eventually I've got roughly n vertices, and this basically, then there's going to be lots of edges at the end over here, connecting these last few levels with one another, but close to V, what I see is just a DRE tree. And so if I ask myself, how does the random walk on this graph look like? In this part of the graph, it will look essentially like a random walk on a tree until it gets to the end of the world, and then it can no longer move forward. And so this result tells you that the speed, the random walk moves away from its starting point with positive speed. And what is the speed? The speed is exactly what it would be on a tree, right? On the tree, there are exactly d minus, actually, this is wrong. This should be d over d plus 1, I guess. There's exactly d over d plus 1. Okay, this is wrong because it's d minus 1 over d with my convention. There's exactly d minus 1 over d. There's exactly d minus 1 edges that take you forward and one edge that takes you back. Is that correct, what I've just said? I think that's correct. Good. So overall, the balance at each step, the way the distance increases by a factor, an additive factor of roughly d minus 1 over d.
So d minus 2 over d, right?
D minus 2, why d minus? Yes, d minus 2, obviously. Thank you. Yeah. So d minus 2, because it's d minus 1 and then minus 1 if you go back. Okay, so thank you, Yuval. So fortunately, this number is going to be of no consequence to us. So this theorem says the following: initially, the random walk moves away from its starting point just like it would do on the DRE tree, but eventually it meets the end of the world, which is here, and can no longer move any further, and so the distance stops there. And so that's what this theorem says, if you like. So again, this is an illustration of the fact that understanding Benjamini-Schramm limit is useful to describing sort of global geometric properties of this graph. So there's a natural thing to guess, which is that if you're interested in the mixing time of random walk on this random graph, then what you have to do is wait until the walk has reached the end of the world. This here, because this is an exponentially growing graph, all the mass, all the end vertices are at the end of this tree, and so before the walk is close to this end of the tree, there's no way for the walk to be mixed, to be close to its uniform distribution, to its invariant distribution. And so, yeah, so based on this work, the conjecture was that the mixing time, okay, this is wrong now, this should be d over d minus 2, I guess. D over d minus 2. This, so the conjecture was that this is exactly, by the time you reach the end of the world, which is roughly here, the walk is close to its uniform distribution. There's no way for the walk to be close to its uniform distribution before, because at that point it's is maybe somewhere here in the tree, and at that point it has only reached very few vertices, nowhere near what it needs to reach in order to be close to its uniform distribution. Does that make sense?
Yeah, makes sense to me.
So actually, this conjecture was proved with the correct factor by Eyal Lubetzky and Alan Sly in 2010. I think this was really a wonderful paper and really a breakthrough in the area. And in particular, this showed that indeed, if you start a random walk, in fact, not only from a typical vertex, but in fact from every possible vertex in this case, there is a cutoff phenomenon, and here is the mixing time. It's given by the time it takes for random walk to reach diameter, which is the diameter of the graph. Okay, so that's roughly speaking the idea. Okay, so this is the detour that I took. How much time do I have, Luis, exactly? I'm already over time.
So, I mean, I guess typically we take an hour, so you would have 2 minutes, but I'm happy to go over. So if you wanted to, I mean, we might lose some audience if people have to leave.
I started a little late, so we can give a few minutes.
That's true. You started a little late. So why don't we say 5 minutes and then, another 10 or 15 for people who really want to hear more.
Okay, that's good. But okay, I'll try not to take.
Well, or up to you, of course. Yes.
All right. So, right. So at first sight, so let's go back to the problem I mentioned at the beginning, that of Erdos-Renyi random graph. And at first sight, the situation looks a little similar between these two random graphs model. Both have tree limits in the Benjamini-Schramm sense. One tree is random, one is not, but maybe that's not so bad. And you can think that a priori, lambda, the mean number of the mean offspring, or the mean degree in an Erdos-Renyi random graph, it kind of plays the role of d, I guess d minus 1. Yes, lambda plays the role of d minus 1. This is always quite confusing, this change between d minus 1 and d. Okay. So lambda playing the role of d minus 1, but apart from that, maybe it's a roughly similar situation. And in fact, there is, in the theory of branching process, there was a landmark paper by Russ Lyons, Robin Pimentel, and Yuval in 2003 that said that if you consider a random walk on a branching tree, so let's call pk the offspring distribution, that would be the probability to have k offspring. And let's condition this tree T to survive, to be infinite. So given this infinite tree, you can consider a random walk on T starting from the root V. So the theorem says that if you do random walk on this tree, then it escapes to infinity at a positive rate. And the rate, so if you look at the distance from the root at time t and you divide by t, then there is a limit in the almost sure sense as t tends to infinity. There is a strictly positive limit, which is not random. A priori, it could depend on the tree, but in fact, that limit is deterministic. It's not random. And in fact, you can compute it exactly. It's given by this quantity here. Okay, let me not discuss this. And so the situation looks very similar. So, we have Benjamini-Schramm limit for Erdos-Renyi random graph, and the random walk on that tree has positive speed. So maybe this can guide us to understand what is the cutoff for random walks on random graph. Okay, so this is initially what we did. Yeah, so you can prove a theorem like that. It's essentially almost the same theorem as what I showed. Maybe let me call this a proposition so that you know this is not the main part of the story. This statement is almost the same as what I showed before. What is the difference? The difference is that now the diameter of this graph has been replaced by the typical distance between two vertices in the giant component of the graph. And the speed of the random walk on this tree is no longer a very simple number like d minus 2 over d, but it's this v lambda corresponding to the speed predicted by the theorem of Yuval and Ross and Robin on the branching tree, where the offspring distribution is Poisson with parameter lambda. So that's why there's a lambda here. Okay, so you can prove that. And this suggests exactly the same thing as before, that maybe this is where the cutoff is located. So initially, the guess that you make when you start a problem like that, this is certainly what we thought, is that the cutoff takes place, and this is the time it takes for the walk to mix, because before that time, there's no way for the walk to have reached order n vertices. Okay, because simply it will take time for the walk to move away from its starting point and to reach the good number of vertices. So we thought that for quite a bit, and we tried to prove it, and eventually we got stuck and realized that actually there was a very good reason we were stuck, because in fact, this naive guess is wrong. So this is what I wanted to explain in the last few minutes of this talk. So something very fundamentally different occurs because the tree that we're talking about is random. And because the tree is random, it has a lot of inhomogeneities. And that makes a very big difference with the case where the Benjamini-Schramm limit is this DRA tree, which is totally regular. The geometry looks the same from every vertex in the DRA tree. That's not the case in a random branching tree. There are some inhomogeneities, and it turned out that because these inhomogeneities, they sort of accumulate and accumulate and accumulate, something very special happens for random walk on this. And really, one way to phrase it informally is that if I look at the places where the random walk might reach, then it's not the entire tree, far from it. In fact, it's an exponentially small fraction of the tree. So if I ask myself, so just to make this more precise, let's call mu m of x the harmonic measure at level m. So what does that mean? It means I have my tree here. I cut it off at generation m. That's the starting point. And I do my random walk. And I ask myself, what's the chance I reach this level through x? So this defines a probability measure. This is the harmonic measure. Okay? It's just, you have a set and you ask yourself, where does random walk exit this set? That's the harmonic measure. And what you notice is that if you, so this is actually an honest simulation, I believe. I think it's taken from the book by Yuval and Russ, if I'm not mistaken. What this is showing is a plot of this harmonic measure as a function of the points on this tree. And what you can see is that it's very far from being uniform. So on a Drarry tree, by symmetry, every point is equally likely to be hit the first time that random walk leaves generation M, it's equally likely to be any point at that generation. But here the tree is not symmetric. And in fact, these inhomogeneities, they build up and they build up. And because of that, the harmonic measure is very far from being uniform. And in fact, what is possible to show is that this harmonic measure is concentrated on an exponentially small fraction of the entire size of this generation. So here's the theorem that formalizes this idea. I think it's in the same paper by Russ Lyons, Robin, and Yuval. I could be wrong. I'm not certain, actually. I should have checked this.
Same paper. Yeah.
It's the same paper? Okay, good. There were a remarkable string of papers roughly by the same authors in a very short period of time. So
this paper is from, well, okay. This paper is from 95, so it's not, this is
not 2003. I'm very sorry about this. Okay, 95. Okay, so the theorem can be formalized in this way. So if you let M tend to infinity, there's a way to formalize a notion of boundary for this tree. So just like in a group, there's a notion of boundary for the group, the Poisson boundary of the group, and which roughly corresponds to, where random walk lives at infinity, how does it leave the graph we're talking about. And let me not say formally what this is, but informally what it says is that if you look at the nth level of a tree, then its total size is lambda to the m, as I explained. That's the Kesten-Stigum theorem. But if you look at the number of points that supports the distribution of the harmonic measure, and then that's much smaller. That grows at another exponential rate, delta, where delta is strictly less than lambda. So with this, I can now actually finish the explaining where the theorem comes from, and it comes exactly from this idea. So what we're going to do is we're going to have this notion of entropic time. So this is going to be the time it would take for random walk on this infinite random tree, so that its distribution, taking into account these inhomogeneities, is of order n. It's supported on roughly n point. And if you do the calculation, then this entropic time, by what I told you, is given exactly by this formula. It is of order log n, and that's the constant we thought we had guessed before, but because of inhomogeneities, there's actually a delay. It's going to take longer for random walk to mix by a constant factor. And so this is the entropic time. And in fact, the theorem is that this entropic time really does govern the cutoff. And so I've not explained a proof, far from it. What I've done is explain to you the numbers that come into play for the statement of the theorem. And what I hope I've illustrated for your seminar in particular is that these numbers, they have a natural interpretation when we think of the Benjamini-Schramm limit. And this is the first thing to understand global properties of the graph is how does it look like locally, because sometimes it simplifies, the geometries become simpler, and nevertheless it mirrors properties that are important globally. Okay, so I will leave it at that. Thank you for your patience and for your attention and your questions. Thank you.
So let's thank Nathanael. Questions?
Okay. There's so much that nobody has questions.
Some of us did our interrupt during the talk.
Yes, that's true. All right. Good.
So I guess, yeah, maybe just to say a few thoughts. So, you know, you have this notion of distance from the, between the random walker and the origin or the starting place. And that's being, you know, that one variable seems to be controlling the total variation distance between where the random walker is and the stationary distribution.
But the point is that one is not enough. You need some this dimension or entropy as well. So the speed is not enough. In the,
okay. Yes, right. Okay, now thank you for clarifying that. Yeah, now I see that.
There is a big contrast between the two situations, and it took us a while to figure it out. And the reason is because really of this inhomogeneities, that somehow the speed of the random walk tells you, it might tell you when the walk has reached the average diameter, but at that time, it continues to live on a very tiny portion of the graph. And that's because the harmonic measure is so small compared to the size of the graph.
I see.
Right. So in the case of a random regular graph, we did not have to worry. This did not come into play because the tree is deterministic and therefore totally homogeneous. And you know, there is no the time that the random walk has reached a distance which corresponds to the diameter of the graph is really the time at which it's uniformly distributed over the entire graph. But in the inhomogeneous case, that's just no longer true anymore.
So, so I guess that this is expected to hold true for other models of random graphs. I mean, some similar statement about harmonic measure and.
Right. So certainly the general picture believed to hold, and so the statement that I made, in fact, is true also. So in the same paper. It's also proved for more general models of random graphs, which I did not discuss. Here it is. This is the so-called configuration model. So even models that are kind of more realistic approximations of the World Wide Web than Erdos-Renyi random graph, for instance. But yeah, so I would say that you know, Erdos-Renyi random graph is maybe the archetypical example of random graph, and there are many things for which we believe it serves as a model that tells us how a high-dimensional random graph should look like in some sense. And I would guess that a similar picture, you might expect it there as well in these situations.
Yeah. Okay. Yeah. Thanks.
So the recent developments, the paper that I mentioned today on the archive, partly kind of builds on this idea of entropic time, that really this is what governs mixing. So this is, I've not read it yet, but this is what I understand of it. It seems to be indeed an important concept.
Okay. You know, I guess if there are no more questions, let's thank Nathanael again.
Thank you.
Yeah, thanks for the very nice talk. I feel like I learned a lot.
Great, I'm happy to hear this. It's not easy to present, you know, a result to right where somehow a lot of introduction is needed and so on. So I hope at least some ideas about random graphs came through. So that was the main part of the what I was trying to achieve.
Yeah, no,
Really nice, very nice picture, big picture.
Okay.
yeah, yeah. So, well, give me something to think about.
Good.
So, okay, yeah. So thanks, and I guess that's it for today. Yeah, thanks again.
Thank you very much. And yeah, I hope the rest of the seminar goes well.
Okay. See you next time.